Hi guys, we are going to focus on simple pendulums as well as physical pendulums, and then that'll be the end of chapter 15 for us. On your blog, you're going to have a couple different things. So you'll have the video link that you're watching now. You have also a PDF that is going to be posted about how do you find the K constant if we have multiple springs, or how would I go about solving a problem if there are multiple springs with different K constants. It's pretty straightforward, and it shows you just the different formulas that you need to know. But if you have any questions about it, post on your blog between now and Monday, so that way I can help answer them then. We'll do the video today, look over that PDF also, and then on Monday, which I'll post this calendar for you as well, which you should see by now. Monday, we're going to be doing problems in class with pendulums, as well as conceptual problems over chapter 15. On Tuesday, we'll do a practice test, and on Wednesday, you're going to have your chapter 15 multiple choice and FRQ test. On Thursday, my goal is to do a diagnostic multiple choice test. The reason I want to do that is because I want to get a sense of where everybody is right now before we start this huge review session and drill and kill with multiple choice and FRQ. With the multiple choice, because we'll have spring break the following week, I'll grade all of them, and it'll give me an idea of where you probably need to spend a little bit more time studying for your own review. Now would be a really good time for you to start forming your study groups to study for this test. It helped a lot last year. If we need to form study groups to go to Starbucks to like once a week, I'm happy to do that as well. So a simple pendulum, we saw it in our lab on Wednesday in class, where it's something that's going to exhibit periodic motion. So we know that it has the turning points. It will also oscillate between those two turning points. It consists of a particle-like bob of mass m, and it's suspended by a light string of length L. The motion occurs in the vertical plane and is driven by gravitational force. So it's really the weight of the mass that's kind of driving then that oscillation. The motion is very close to that of a simple harmonic oscillator, and because we are going to model a simple pendulum as an oscillator, we want to assume that the angle that that pendulum is going to be swinging is going to be 10 degrees or less. And remember, we called that the small angle approximation. So for our test and for us, always assume that when they talk about a simple pendulum, that the small angle approximation is in play. The two biggest pieces about pendulums that they're going to want you to know, both simple and physical pendulums, is what is that pendulum? What are the variables that can affect the period of the pendulum for both simple and physical pendulums? So let's look at the simple pendulum first. I have the bob that's here, which is just your mass. I have the length of the string here, we'll call that L. And then it's going to move at some arc length that we already know, we'll call that S. The forces that are acting on it. So if the length of the string is here, think about that if we're talking about torque. So let's just go in the torque direction for a second. If I think about torque, I know that torque is equal to force times or cross that lever arm radius. So here would be my lever arm. That would be the length of the string here. And remember that to have torque, the lever arm and the force have to be perpendicular to one another. So the weight force is going to act straight down from this bob. So that means I need to take into account which of the components will be perpendicular to that lever arm. And that's going to be the mg sine theta here. Because if theta is right here, I have my weight force vector down. Theta will be here. Here then is mg cosine theta, here's my mg sine theta. So these two, since they're perpendicular, this component of force, the mg sine theta, is going to be that component of force that I need to focus on. Okay, so hopefully that makes sense, that it won't be all of the weight force, it has to just be a component, because I have to think about what force is really going to cause that to oscillate. When we want to derive the period for a pendulum, there's two different ways that we could do it for a simple pendulum. I like one way, the first way, probably better than the second way, because it just seems to be a little bit easier. The second way, though, focuses and makes you go back to how do you write a differential equation for acceleration of a pendulum, for velocity of a pendulum. And we have to use the second way when we're talking about a physical pendulum. So I'll show you both ways, just so that way it will help us out a little bit. Okay, so pretend like the next couple slides don't even exist to you, because we're going to derive all of this crap together on the board. And then we'll get to the physical pendulum. Okay, so stay with me here. Let's say that we have our bob that's attached to some string that we'll call length L. Okay, theta is going to be right here, and it's going to move at some arc this way. Weight force goes straight down, so I know that the weight force is there, but I need to think about the force that is perpendicular to the lever arm if I'm thinking about torque. So because of that, we're going to use mg sine theta when we're talking about force. So for the first way, what force is causing the bob, or the mass that's attached to the length of the string, what force is causing the pendulum to oscillate? Remember, that's this restoring force, and we call that, we base that on Hooke's law. So I wrote Hooke's law here. I have F is equal to a negative Ks. I used S instead of X because really it's the arc length that that pendulum is moving, so its displacement needs to be in the arc length, so we call that S. The force that's causing it to move is that component force that's perpendicular to L. So I said that's mg sine theta. I called it negative though, because it's making it go in that counterclockwise direction. So hopefully that makes sense as well. And that's going to be equal to a negative Ks. I don't like S because my goal is to show how length is somehow dependent here in this pendulum. I do know that arc length is equal to r theta, which means really arc length r here is just that length of the string. So I called that S is equal to L theta. So I plugged that in here. So now I'm at mg sine theta is equal to KL theta. Hopefully we're all on the same page. I just wanted to come up with an expression for K. And I did that because, well, we'll see in a second. My goal is to get to the period of this pendulum for the simple pendulum, but I first need to find something for K, and we'll see why. Once I'm here, I just took everything and moved it over to this side to get K. Because we're assuming that theta is less than 10 degrees, if I take the sine of theta, it's going to be like it's just theta. I'm not going to get very much different results there. So it's really like sine theta is just going to be approximate to theta. So, and that's just because of our small angle assumption that we're taking. So I changed this to say just mg theta over L theta. So now the sine is gone, because sine theta, again, it's so small, we're just assuming that it's really just theta. Thetas will cancel out, so K is equal to mg over L. Why did I want us to do this? I wanted us to do this piece because we know something about angular speed, and we also have an equation for calculating period. And I calculate period by taking 2 pi over omega, which we said is angular frequency or angular speed. I don't know what omega is though. But earlier in the chapter, we came up with our own formula that says omega is equal to the square root of k over m. I think I have that on next slide. Yeah, I do. So we came up with omega is equal to k over m. Well, now I know what k is equal to because we just found that out on that last page. And I know that t is equal to 2 pi over omega. So I said, if omega is equal to the square root of k over m, let me plug that in for omega. So I get 2 pi over the square root of k over m. I need to simplify that a little bit more because I don't like the radical in the denominator. So I said 2 pi times the square root of m over k. I don't like that either because now I can plug something in for k and try to simplify it down even more. K, we already said, was equal to mg over L. So let me plug that in here for K. I did that here. So now I have 2 pi radical m over mg over L, so I just plugged that L up there since that's what we would do. Masses cancel, so then the period for a simple pendulum should be equal to 2 pi times the square root of L over G. In your lab today with simple pendulums, you found mass did not affect the period at all. Theta didn't affect the period at all, but length did. And so this derivation just shows you that length is really the only thing that period is dependent upon for a simple pendulum. It's a really good multiple choice question that they could ask you, and then it's also a possible FRQ question that they could ask you too. So that's the first way in which I can derive the period for a simple pendulum. Let's look at another way. So I made you think about torque before, and thinking about torque, we already said that that would be a force cross the lever arm, R. We also know that torque is just equal to I times alpha, which is just the angular acceleration. And remember what I is? That's that moment of inertia. So this equation here, if I'm looking at this, I know it's a lot, guys, but just follow me from starting here. So torque is equal to I alpha, and I is that moment of inertia. Again, alpha is angular acceleration. That's the rotational analog of Newton's second law. So if I know that torque is also equal to R cross F, then before, when we looked at that simple pendulum, remember we said if the lever arm is L, which would be the length of that string, then the force that's causing the force that's causing the torque has to be perpendicular to the lever arm L. And we said that last time that that would just be mg sine theta. It's a negative because it makes it move in a clockwise direction, which would be a negative. So I have a negative mg sine theta times L, so there's my force times my lever arm, is equal to I alpha. Let's assume again that theta is that, we're assuming that small approximation assumption. So because of that, I took out the sign and I said a negative mg theta L is equal to I alpha. We have also set up earlier in the chapter some differential equations for acceleration, for velocity, and for displacement, or for position. So before we said acceleration is really the same thing. So I was right here, let me just look right here first. So before we know, acceleration is really just the second derivative of position. Because it's the second derivative of position, we went ahead and derived this last week. So we got a negative omega squared times the amplitude, and then the cosine of omega t plus phi. If I have alpha, alpha is really the same thing as the second derivative of angular displacement. So because of that, I want to think about alpha as being the second derivative of theta with respect to time. So still the same thing over here. Now I'm just trying to make my own differential equation for finding omega. That's my goal right now. So I set this, and I just want to say the second derivative of theta is equal to something. So I divided by I, and then I gave this piece here, and then I just wanted to see this piece times theta. So this is what I was left with. I'm going to make kind of my own assumptions here and use it in a certain way, where if this is based on alpha, because we're talking about angular acceleration, then let me make this whole entire piece here omega squared. And then theta, I'm going to make that equal to a cosine times then whatever phase shift that you have, omega t plus phi, or it could just be omega t, okay? Why did I do that? Because I can do that. Because this omega piece here just tells me, it's kind of like that k constant for spring force. This is just giving me where I could find my angular frequency, but only using a differential equation form. So we're going to set this equal to omega squared. All of this then will just be your A cosine omega t plus phi. I really don't need this piece because my goal is to just find the period. And we know that period is equal to 2 pi omega. I said that this whole thing here, we're going to set equal to omega squared. So if this is equal to omega squared, omega just has to equal the square root of all of that. So if this is omega, I'm going to plug this in then for period. I come over here, I have 2 pi over radical mgl over I. I want to simplify that down because, again, I don't want the radical in the denominator. So then I get 2 pi times radical I over mgl. I don't like that either because it's not simplified enough. So this is where I left off, 2 pi radical I mg over L. If I'm thinking about just the moment of inertia definition in general, if I'm thinking about L, then instead of mr squared, I could use ml squared. So let me just plug in that very generic formula for I, which I said is ml squared. So I have 2 pi times the square root of ml squared over mgl. Masses cancel. L cancels down here. I'm left with 1L over here. So I'm left with 2 pi times the square root of L over G. So we can take more of an algebraic approach to come up with using forces to get the simple pendulum period. I could also take more of a differential equation form and try to find the period of a simple pendulum this way. But both ways set us up so that we're always seeing that a simple pendulum's period is only really based on the length of the string. Okay, so that's a simple pendulum, but we also have one more pendulum, and that's called a physical pendulum. This is just to sum up that the period and frequency of a simple pendulum really truly only depend on length of the string and acceleration due to gravity. It is independent of mass. It is independent of theta for us because we're assuming that small angle approximation. Okay, for a physical pendulum is a little bit different in that if we have a hanging mass, we have a hanging object and it oscillates about some fixed axis that does not pass through the center of mass, and the object can't be approximated as a point mass, we call this a physical pendulum. So we can't treat this as a simple pendulum because usually a physical pendulum is more of an object that's kind of, it's not necessarily right at its center of mass. So we need to try to treat it as though something is moving about its center of mass. So it's still the same idea in that I'm going to have some mass and it's going to be oscillating back and forth. It's just that I want to think about how that oscillation moves based on the object's center of mass. Let us derive the period for that type of pendulum. On Monday, I'll try to come up with something that we can see the oscillation or the amount of period that would be for a physical pendulum. So that way you can have that idea versus a simple like you saw in lab today. Okay, so for a physical pendulum, it is so much, it's very, very, very similar to what we did with a simple pendulum. I go back to thinking about, because this one I'm going to use that second approach, that differential equation approach. So go back and think about net torque. I have R cross F, and that equals I alpha. I know that the lever arm is going to have to be, for the lever arm, it's going to have to be perpendicular to the force that's causing the oscillation. That force that's causing the oscillation is still going to be mg sine theta. And it's negative again because it's causing a clockwise rotation, which then, of course, gives us that negative sign. But instead of using R, instead of using L, I used D. D is going to be the distance that the object is from the center of mass. So let's say, for example, you have a long, uniform thin rod that's rotating about an axis point here. The distance d would be from where that pivot point is to the center of mass. So we're going to call that d. Okay? Again, where am I thinking the force would be taking place? That force is going to have to be the weight of then that beam, which here is just straight down. But I need the force, or the component of force, that's perpendicular to that lever arm D. So that has to be the sine, which would be mg sine theta. Okay? So hopefully we're good with how I got that symbol D. So all of that is going to equal I alpha. Again, let's assume that we're approaching this with our small angle approximation. Sine theta is really just approximately theta. So mg theta times d, a negative mg theta times d, is equal to I times, I went ahead and just said alpha is the second derivative of angular displacement. And I know that angular displacement, or that second derivative of angular displacement, can also be thought of as just a negative omega squared and cosine of omega t. I set this equal just to my second derivative of angular displacement, so I got a negative mgd over I. And all of that then would be times theta. Just like what we did on the last one, I said that this, I'm going to just set this equal to omega squared, and this is going to be set equal to theta. So that way I'm getting everything that I need of all of my variables that are here in that differential equation. I don't think I mentioned this on the last one. Since this is negative here and this is negative here, I don't have to think then about the rest of this as being negative. We'll just think about those as being positive entities. So omega squared is here. This is my a cosine of my phase shift. So then if I want to know period, again, period is equal to 2 pi over omega. I need to know what omega is. If omega squared is mgd over I, then omega has to equal the square root of all of that. So then I said t is equal to 2 pi over omega. That's going to equal 2 pi over, I plugged in omega down here. Don't like that in the denominator, so I'm left with the period is equal to 2 pi times radical I over mgd. So this is showing you that whatever physical object this is, whatever this physical pendulum may be, it's dependent on a lot more than just this simple pendulum. So a physical pendulum is going to be dependent on the moment of inertia that this object has, as well as the mass that the object has times acceleration due to gravity times the distance that it is from the pivot point to its center of mass. So this one is a little bit more complex. I think if this were a multiple choice question, they're not going to ask you to derive it. They're just going to ask, what's the formula for the period of a physical pendulum? So if you just know it, we'll get that one right. Same thing as they could ask you, probably more in words, with a simple pendulum, given Roman numeral 1, 2, and 3, what are the possibilities of affecting the period of a simple pendulum? And then they could ask you that way. So hopefully we're good with finding the period of a physical pendulum and a simple pendulum. Again, you have a PDF talking about if you have multiple springs, how would you go about solving a problem that way, or finding a K constant for that. And again, you'll also see your calendar on your blog as well. I hope you guys have a really great weekend, and I will see you on Monday. Bye!